Hi, and welcome back to the last part of the Basic Equality Bootcamp. So for this part, we are going to look at something called Equational Reasoning, which is a nice way to write your equality proofs so that they are readable and easy to see, although a little bit verbose perhaps. And the way to get access to this is in the Equality Reasoning module, which in itself is part of the relational binary propositional equality. So first of all, here I've just given ourselves multiplication because we are quickly running out of facts about addition to prove. So let's do multiplication as well. It's defined as you expect. 0 times m is 0, and suc n times m is just m plus the rest of the multiplication. So we just do 1m for every n that we have. Right? And let's say that we want to prove that addition distributes over multiplication. So n plus o times m is the same as n times m plus o times m. Right. So let's prove this. And as usual, we ask why is it stuck? And there's a few reasons why it could be stuck now, right? But we see that one good reason why something is stuck is that we don't know what this n is. So that's why the plus is stuck here, which in turn means that that's why this whole thing is stuck. And that's also why this is additionally stuck, because this is also defined by looking at the first argument. And this bit is stuck because the O is stuck, but we don't know what. It looks like looking at the n is a good idea, so let's do that. Okay, let's look at the 0 case. What do we have to prove now? Well, reassuringly, it became something simple. That's REFL. Let's look at the successor case. This doesn't look so simple, right? Let's try REFL in case we're stupid. No, that didn't work. Okay, so what we do in these cases, if we want to do this step by step, is that we, first of all, I use the delete this goal, and then I go to a new line typically, and I say begin as a way to start the equational reasoning. And then I'm going to leave a hole here where I'll fill in later. I'll do equality sign with a hole for the proof, another hole, and I finish the whole thing with \QED, which gives us a little black box. Okay, so this is how we lay out these things. So start with begin, we finish with QED, and then here we put the terms that we want step by step with proofs for why they are equal to each other. So the first thing I'm going to do is I'm going to solve these two goals, solve constraints, which will fill in what this have to be in order to be a proof of the right thing. So we see that this is what we have to prove. Right? It's the same thing that we have up here, but n has now been instantiated to suc n. Okay, so now we can just start from the top or from the bottom and try to work towards the other side. So the first thing we see here is that this suc n plus o is actually going to reduce to something. Right? So what I typically do is I go to the beginning of the line, Control A, and then I kill the whole line, Control K, and I kill the next line, and then I yank it out again twice. That's Control Y, new line, Control Y, and then I change this to what I want to change it to. So in this case, I would like to do the reduction of the plus. So this should be the same thing as putting a suc outside the whole thing, right? And then I might as well do the next step immediately, because now here I have a suc times something, right? So by this line, that should be the same thing as doing m plus and then another addition like this. Balance my brackets. Okay, so this step is all happening by computation, right? So REFL should be a good enough proof of this, and it is. That's reassuring. And there is a special syntax for this. We can just not give a proof if it's REFL is a valid proof, just like this. Okay, so that's as far as we get just by computing, but we're not all the way where we want to be yet, right? So let's see what we can do next. Well, here is something that looks like a recursive call, right? This is the same thing again that we're trying to expand to something else. So I'm going to expand that to the thing I want it to be. which is n times m plus o times m. Okay, so here now I have to give a proof why this is equal to this. And I see that, well, this m plus at the beginning is the same, so that looks like a job for Kong. Okay, and this is the thing which is m plus and then the rest of the argument. But I still have to give a proof here why the rest of it is equal to that. Just this thing, but that's exactly a recursive call, right? So that's m n o. That does it. Okay, so now we made some progress, but we're not all the way here yet, right? So let's see, is there anything else we can do? There's nothing obvious we can do about this, I think. So what I typically do in this situation then is I go to the other side and try to work backwards. And here there is something obvious to do, right? Because here again we have a suc n times something. So this should reduce to m plus n times m, like that, right? This happens by computation, so readable works, or we can just leave it out like this. Okay, so now we can compare these two, and now they're starting to look like each other, right? They are exactly the same, except that they are bracketed in different ways. But we did have the plus sock proof, which told us that we can do things in different orders. So in this case, the first thing we have is m, the second thing we have is n times m, and the third thing is o times m. Right, so let's see. So that doesn't quite match what we want, because it's annoyingly the wrong way around, right? Our left-hand side is the goal's right-hand side. So we're going to see in a future video how to make sense of this, but for now there's a special combinator which I never remember the name of, so I always go and look it up. And it's the one which has this little funny symbol. So if you put this one here, I have no idea how to type it. You could find out if you wanted by doing this. So apparently you type it by doing \u. Okay, good to know. I always look it up. So if you add that there, then that reverses the direction that you need for this proof. So now we see that everything is working, and we are happy. We can reload that, and it's all fine. So this is a nice way to lay out your proof so that it's a little bit more readable, and also you can work step by step without knowing exactly what all the proofs are going to be. So you see that I had no clue overall what I was doing. I was just working locally and seeing what made sense. So these are the two main takeaways. You have to open this in order to get access to it, and you have to remember there is begin and this symbol. So you type these things by doing \, equals, angle brackets, and close angle brackets, \, angle brackets, no. Yes, \, angle brackets. And then \, the other way. And this one is \QED. So if you open this module, you get access to these things, and then you can lay it out like this, and you can work on your equation step by step. And often it's good to do it from both directions.